So the first technique I want to do is just substitution. Because I have what value of d right there. D is b plus c. So what I'm going to do is just put b plus c in for d there to get rid of one of my variables. So I have 7 minus 3 times b plus c minus 7b equals 0. 7 minus 3b minus 3c minus 7b equals 0. 7 minus 10b minus 3c equals 0. And then I have 2 plus 7b minus 6c equals 0. So that equation gets us here, and then this equation. And it probably helped if I made my sevens the same way. And then a dramatic pause for anyone to correct the Carol's error I've made. So now I have two equations, two unknowns. So I think I will, solve for b. Oh, I can divide by 10 easily enough. I'm going to solve for b in this equation and plug it into the next one. So if I solve for b, I'm going to add it over to the other side. So I have 7 minus 3c is equal to 10b. Then I divide by 10, and I have 0.7 minus 0.3c is equal to b. Substitute that into the other equation. I have 2 plus 7 times 0.7 minus 0.3c minus 6c equals 0. 2 plus 4.9 minus 2.1c minus 6c equals 0. 6.9 minus 8.1c equals 0. 6.9 equals 8.1c. Now 6.9, 8.1 over 8.1 is not an acceptable final answer, because a decimal point is like a fraction bar, and I want only one fraction bar per number, or at most one fraction bar per number, and at most one fraction bar per unit. But 6.9 over 8.1 is
0.85.
0.85?
Yep. Volts. Right? No.
Nope.
What is, oh, it's current.
Yes.
Amperes.
Yes. So I'm going to write that over here. So we have C equals 0.85 amperes. Questions about how we got that?
Just to clarify, this is still method 1, the 1 current per path?
Yeah, the methods there are just how do you get the equations.
Oh.
This is the math piece of it.
Which is the same regardless of how you do it.
Yeah, whichever method, whichever one comes up with the equations, we could still use this same math technique.
When you introduced this, you said that you were doing the first method, but it seemed like we did 1 current per loop, right?
We did 1 current per path.
Oh, okay.
Because getting from here to here, there's 3 paths.
Mm-hmm.
I have 3 currents.
Okay.
If I did 1 per loop, I have 2 loops.
Oh,
And so there would be only 2 variables.
okay, I see. Thank you.
I'm just catching up.
I will say the biggest mistake students make, besides, there's careless errors, lots of places for that. But the biggest mistake is sort of mixing and matching the 2 techniques. So my advice is, after you've seen them both, pick one of them, even if it's a flip of a coin to figure out which one you're going to do. Pick one and learn how to do that technique. All right, so we have C now, and I have an equation here for B. So plug and chug. So this becomes 0.7 minus 0.3 times 0.85. So 0.445.
That's exactly right.
All right. And then we have an equation here for D. It's just the sum of B and C. So doing the fancy math there, we get 1.295.
Yes.
Now notice we got all positive answers. That tells us that I guessed the direction correctly for each of the currents. .85, was that exact?
No.
Okay,
There were more decimal points. I'm sorry.
no problem.
This was 0.851 repeating basically.
Okay.
Something like that.
All right, we're about to do this another way. Any questions on this before we do Kramer's rule? I still want that. Actually, we need those. So I'm going to rewrite the equations up here. So D equals B plus C. And then we had 7 minus 3D minus 7B equals 0. And 2 plus 7B minus 6C equals 0. Quick check, make sure I didn't get a sign off. Those look the same to me. All right. How many of you have dealt with Kramer's rule before? All right. How many of you have dealt with matrices before?
10 years ago.
All right.
I probably
Determinants?
have, I mean, I remember the word, but I don't remember it.
Okay. Determinants?
That also sounds
I also
familiar.
remember that word, but.
Right.
Okay.
Woo.
Typically, the way it's taught today is that when you deal with matrices, you also learn determinants about the same time, and you learn Kramer's rule shortly after that. It turns out Kramer's rule, or determinants were used before they ever figured out matrices, which seems strange to me. But so let's talk about just determinants. This is just the pure math bit right now. So if I have a 2x2 determinant, and I'm just going to stick numbers in here of 2, 4, 3, 7. We'll make one of them negative, -7. The way you solve a determinant is, the pause there is, I was about to say you start in the upper left-hand corner. For the purists in the group, you can start anywhere, but the technique that I am going to do every time for this group is I'm going to start in the upper left-hand corner, and I'm going to go across the top. There's some more complicated ways of dealing with it, but I'm just going to do one way every time. Starting in this corner, working my way across. I'm going to find the determinant of this. So I start in the upper left-hand corner and I write that number down. I now block out the rows and columns that that number was in, and what I'm left with, I find the determinant of that number. This is not absolute value, by the way, it's determinant. And then minus, and it's negative because the first term is, this is positive, then negative, then positive, then negative, and it's going to go like that. So minus, and then I do the next number, 4. I block out that row and that column and I write down what's left over. And I find the determinant of that. Conveniently, the determinant of a single number is just that number. So this becomes 2 times -7 minus 4 times 3. So -14 minus 12, -26.
So we don't work across the bottom numbers?
Nope.
So even if this was a really large group, it would just be across the top for this method?
Yeah. I could have picked any row and started working my way across. The question would be, is the first one positive or negative if you're not starting in the upper left-hand corner? It's also possible to start in the middle and work your way out, but
Right.
it,
So what if this was 3 by 3? Then what would we have written instead of just -7?
whatever's left over, we'll do a 3 by 3.
Oh, okay.
So, well, you end up with a number and then a 2 by 2 minus the next one times it with a 2 by 2 and then. All right, so if you do 1, 5, 6, 1, let's make it a -6, 2. What is the determinant of this 2 by 2? And if you see the shortcut, run with it.
I assume the shortcut has to do with signs.
Well, I mean, signs are involved. Right. I'm assuming you have something.
16?
What'd you say?
I got -16.
I got 16 as well.
It should be positive 16.
Oh. Nice.
Ready?
16.
Way to be the voice of one.
I had to be special.
Upper left-hand corner, 5, times what's left over, 2, minus,
I put why, I don't know, I guess I don't understand that part. Yeah, I thought it was -2. I
No,
don't
just
understand that.
just the number there.
Okay, oh.
Because I officially am blocking out that row and column, what I'm
Okay,
left
I
with is
see
just a
it
2.
now. I see it.
Oh, yeah, that was -4 because that number was
Yeah.
negative.
Yeah.
Okay.
I see it now.
Now the shortcut with a 2 by 2 is ultimately it's just that diagonal minus that diagonal.
So why is the -4 on the one that was, why is it -4 on that one?
Because when you're working your way across, the first thing is that's positive, then the next one's negative, the next one's positive, the next one's negative if it's a 4 by 4. It's just the way they're solved.
Gotcha.
I never got into it deep enough to understand why it does that way, I just know that's the way they do it.
Okay.
I'm trusting the math people.
Might as well.
There's supposedly a 100-page proof for why 1 + 1 = 2. So far, I've just trusted them. There used to be a 2-page proof, but then somebody found a flaw in it.
My life's work proving 1 + 1.
All right. So 16, I think we have agreement on that. All right, so let's tackle the 3 by 3. 4, 6, 1, -1, 2, -3, 8. What have I not done? 5, 7, 9. They don't have to be single digit numbers. That's what I'm doing. All right, so I'm gonna start in the upper left-hand corner, 4. And then times the determinant of what's left over, -3, 8, 7, 9. Minus, because it's the next one, 6. I block out that row and that column, I'm left with 2, 8, 5, 9. Plus because it's the next one. Negative 1 times, block out that row and column, 2, negative 3, 5, 7. So pause for people to ask questions if they're not sure where I got these numbers from, or to correct any mistakes I made. We'll write that down. See if I can make this darker. Alright, so now we've got a bunch of 2 by 2s, and we just did those. So this becomes 4 times negative 27 minus 56, minus 6 times 18 minus 40, plus negative 1 times 14 minus negative 15. Oh, and now I'm dealing with bigger numbers. So 4 times negative 83, and 6 times negative 22, plus negative 1 times 29. 332 negative plus 132 minus 29. Negative 229.
That's what I got.
Okay.
So just to clarify, this was an alternate method to doing what we just did to solve these equations, right?
Right.
I'll probably be doing it the other way.
I've done this enough that in a typical class, one person, they'll have at least one person doing one of the techniques. And then a few who try to sort of mix and match.
Not doing that.
All right. The shortcut. Recognize that this negative 27 here comes from negative 3 times 9. And then I combined this first, but I could have distributed. I could have done 4 times negative 27, which would just then be 4 times negative 3 times 9, which is that diagonal right there. The negative 6 times that 40 comes from 6 times 5 times 8, or 6 times 8 times 5, sort of going around the corner. And then over here, we've got a negative 1 times 2 times 7, negative 1 times 2 times 7. Some people find it helpful. 4, 6, negative 1, 2, negative 3, 8, 5, 7, 9, just to repeat the first 2 rows. 4, 6, 2, negative, sorry, first 2 columns, 5, 7. And then I multiply those together. Plus, let's go ahead and do that. So 4 times negative 3 times 9. 12 times 9, negative 108.
Yep.
And then 6 times 5 times 8 is plus 240. I think. And then negative 1 times 2 times 7 plus negative 14 minus, I go to the other diagonals. That is 15 8 times 4 times 7. $222.
$224.
And then 6 times 2 times 9. What's one of them? So starting up, it's the left to right, going down, add those up, minus the ones going in the other direction. And I hope you get negative 229. If not, there's a Carol's error somewhere. I will say it is a little bit easier when we actually use it to apply to this, because there's going to be some zeros that show up, and zeros just make life a little bit simpler. And Wesley's about to tell me if I made an error.
No, I'm just making sure that I can do this, or I mean, not just go through the steps.
Okay. Besides the error that was already pointed out. All right, so let's actually use Kramer's rule. When I have a system of equations here, if I want to apply Kramer's rule, what I need is all the variables on one side and all the constants on another. When I say constants, I'm not talking about that 3 right there. I'm talking about the numbers that have no variables attached to it. So basically, those two right now. So I'm gonna rearrange the equations so I have something times D plus something times B plus something times C equals a constant. So the first one, well, I'm just going to bring B and C over to the left-hand side. So I have 1D minus 1B minus 1C equals 0. My second equation, again, one of those things with me, I just prefer positive numbers over negative numbers. So I'm going to add my 2 variable equations over to the right and then flip my equation around.